This is a quick video related to my assignment for some topic questions in AP Classroom from Unit 2. This is the question number 1. I've already solved them, so I'm going to walk through them. You can take a quick pause if you need to think about what I've gone over. So this first one has a graph that shows speed versus time, and we read the problem, and it says an object of mass 10 kilograms is released from rest above a surface of a planet such that the object speed as a function of time is shown in the graph above. And then the question is, the force due to gravity exerted on the object is most nearly, and you have to calculate it. So we need to know force of gravity on the planet. And since we don't know what the planet's mass is, we can't calculate what little g is. On Earth, it's approximately 10 meters per second squared. But if we visualize the situation over here, this is what's happening. We have an object, it's dropped from rest, and the thing, it's accelerating downwards towards the planet, and that acceleration is due to gravity. And this graph shows that speed versus time. So we got to look at this graph, and every time you have a graph, they don't give it to you just for fun. They give it to you for a reason. And so it's speed versus time. And every time you are given a graph, you ask yourself, what are the units of area and slope? Area's units is height times the base. So pretend you drew a box on that. And the height is in units of meters per second times second. And that gives me a unit of meters. And that gives me some type of displacement, delta x. That's not what I'm looking for. That's great, it's useful, but I'm looking for acceleration on that planet. The slope gives me rise over run. The units are in meters per second squared, and the slope of that graph gives me acceleration. That's very helpful because I'm probably going to need that acceleration to determine the force of gravity. Well, what is the force of gravity equation? It's Fg times mg. I know the mass, I need the acceleration due to gravity, which I then use the slope to calculate. I picked a nice easy point. The rise was 7 meters per second. The run was 2. 7 divided by 2 is 3.5. I then plug in my mass. I find that it's 35 newtons. The next question, a 2-kilogram object, once again, is released from rest near some planet that its gravitational field is considered to be constant. The gravitational field is what causes the acceleration due to gravity. The mass of the planet is unknown, and the object speed after following for 3 seconds is 75 meters per second. Air resistance is negligible. Calculate the weight, which is by definition the same as force of gravity in a 2-kilogram object. So here I've listed my knowns. They give me that mass, my initial velocity, final velocity, and time is equal to 3 seconds. Here's my picture, here's my planet. And then they want to know, again, the weight. The definition of weight is what is the force of gravity? I need to know that little g. Well, in this case, they didn't give me a graph. They gave me 3 things. 54321 will tell me that I have 3 things, and I can calculate the acceleration by using my kinematic equation, which I've done over here in blue. And so my favorite equation, which is the first equation on your equation sheet, top left, is rearranged for acceleration, plugged in the 3 things they gave me, and I found acceleration of this object as it fell for 3 seconds from 0 meters per second to 75 meters per second to be 25 meters per second squared. I can then plug in that value into my weight equation, which is equal to Fg on that planet. And so I find the weight of the object to be 50 newtons. Number 3, these are not my favorite. I am very bad at these. Nope, never mind, that's not the one. Okay, the book is at rest on the top of the table. A student makes the following claim. An attractive electromagnetic force is exerted on the book from the table. And this force can also be classified as the force normal. So here's my drawing of a book on the table with force normal up, force of gravity. Force normal, in class, I've talked about what is force normal, where did it come from? We have molecular structures of the 2 subjects touching one another. Those molecular structures are made up of atoms. Atoms have on the outside of them electrons flowing around. They're both negative charges. So negative charge repulses another negative charge. So force normal is always a repulsive force. So this person's claim as that the fact that it is an attractive force is incorrect. So I'm not even, when I'm doing this, I'm not even going to read question A or answer A and B because it said that the student was correct. So don't even waste your time reading it. So now I'm going to look at the two items that said they were correct. D shows that the claim is incorrect because the charge particles of the table, did I do that wrong? The charge particles of the table exert an upward force on the charge particles of the book. I think I actually circled the wrong answer. So that looks right. Oh, I see what I did. That is wrong because they said upward attractive force. Again, it's an upward repulsive force. So just a little bit of vocab to try to trick you. So be very careful to read the words. So C was the correct answer. Number 4, I have the situation. They give me a free body diagram of brick number 2. They tell me some things. The forces on that block brick 2 is an upward normal force, a downward force on brick 2 by brick 1, and a downward gravitational force. How many of the forces, if any, are considered contact forces caused by microscopic interactions? Microscopic interactions are due to those electrons of the molecular structures of the components. They're considered contact forces. So force of gravity, as you know, hopefully, is from the earth, and it doesn't have to be touching the earth to be present. I can drop something and it's still there. It is considered a field force. So there's only 2 forces, force normal and the force of brick 1, which is in contact with brick 2. So there's only 2. All right, moving on to this situation. We have that drawing right there. A block slides to the right on a rough, that means there's friction, sliding, that's force of kinetic friction. The forces exerted on the block are shown above. I always draw a picture, so I have a velocity to the right. I know that it's sliding to the right because force of friction is to the left. Which of the following statements about the frictional force exerted on the block is true? So I'm thinking about force of friction and reading each item and determining whether the statement is true. It is the only force that acts on the block that's caused by microscopic interaction. That is not true because force normal is also a contact force caused by microscopic interactions. It does not depend on the materials that the block and the surface are made of. Force of friction has mu sub s or mu sub k in it, which is completely 100% related to the materials of construction of the 2 substances. So that's wrong. It does depend on its material. C, it's caused by gravitational interactions between the atoms in the block and the atoms in the surface. No, that gravitational interaction is only with the earth. It is the sum of all the microscopic contact forces between the bottom of the block and the surface. That's the only option it could be, but if you think about it, force of friction is equal to mu sub s, or mu times force normal. And so we can consider that the sum of all those forces, okay? But once you know that the other 3 are wrong, circle it and move on. This is the problem that I have with number 6. I struggle with these, but I'm going to keep going over them, and you're going to see me fumble through them all year long. It's my weakest subject related to AP Physics. A student must design an experiment to determine the relationship. So I'm trying to focus on trying to develop a process on how to do these. So this word relationship is important, so I'm starting to realize. So I need to determine the relationship between mass and acceleration and the mass and acceleration while under some force. I have to have a net force is in order for that to be accelerating. So a net force, how about I say this? Net force is there and it can't be 0. Okay. In order for me to do this. And so what's going to happen when I go through this, I need to find a situation that changes one and look at the other 2, changes something, and changes the same thing over and over again. and then measures the other two items. Okay. So I'm starting to see. All right. We drop different masses from a known height above the ground for multiple trials, different masses. So I'm changing masses. Great. Okay. Such that they reach their respective terminal speeds from different heights. Oh, from a known height. So I'm just taking a mass, different masses. So I'm changing the masses, but I'm keeping it from a known height. So it's under acceleration until it reaches terminal speeds. Terminal speeds are such that the air resistance up and the force of gravity down equal one another, and the acceleration then goes to zero. I measure the time it takes each object to reach the ground, and then I record the mass of each object by using a scale. So I'm not really determining the relationship between force net and the acceleration of some mass, these masses, because I've reached a terminal speed and acceleration is zero. Letter B, slides objects of different masses, so I'm changing masses, across the same rough surface. So I'm keeping the, hopefully the force of kinetic friction the same. Well, that's not true. Force of kinetic friction equals mu sub k times force normal. So mu k stays the same, force normal is changing as mass changing, so that each travels at a constant speed. So now I don't have a net force anymore. While under the influence of a force of kinetic friction, then measure the force required to keep each object at a constant speed by using a force sensor, and record the mass of each object by using a mass scale. Perform this experiment multiple times with different objects. I'm not really determining how net force affects acceleration because I'm keeping my acceleration at zero. C, place an object on a rough surface so that the object's at rest. Use a force sensor to exert a force on the object just until after the object overcomes the force of static friction. Record this force. All that does is determine maximum force of static friction. All right, now look at D. Slide an object of known mass across a rough surface. Apply a constant force, and that can be measured. Okay, a constant force that can be measured. Use a motion detector to determine the speed, which as it goes across, and that allows me to determine the acceleration, because if I have a motion detector, I can actually put some position versus time curves on it and determine velocity and determine how the velocity changes and determine how the acceleration is present. So constant net force net, and I keep known mass, same mass, change the force net. I keep getting mass and I have changes the force net and I get some measurement of acceleration. So D is the correct answer. I'm just going to tell you, these are probably hard. These are very hard for me. So don't feel bad if that's hard for you as well. Okay. Number 7 should not be hard. We have a tennis ball. It's thrown against a wall. It's fixed to the ground. The ball bounces off the wall. How does the force exerted by the ball on the wall compared with the force exerted by the wall? Okay. How does the force exerted by the ball on the wall compare with the force exerted by the wall on the ball? Lovely that they make those rhyme. So if you see this situation right here, Newton's third law, even though the wall is fixed and stationary and the concrete's super heavy and has a huge mass, Newton's third law says the force that the ball puts on the wall is exactly the same magnitude as the force that the wall puts on the ball, and they are opposite. So the answer is B, because they have the same magnitude. Number 8 and 9 had a lot of algebra in it, but I will tell you that you should be able to do this algebra very quickly because it should be very straightforward. This is a situation of a block that's sliding to the right, because I know it's sliding to the right. How do I know? Because I actually have to solve for its acceleration. Friction's to the left. That means velocity must be to the right. Okay. They want me to solve for acceleration. Now I'm going to tell you right now, a trick that I have found is quickly look at the answers within the multiple choice and look inside the types of answers. And you see that I have to basically use Newton's second law and sum all the forces, and I've got to get rid of all these symbols. So you don't see F in here. All right, you don't see friction. You don't see force normal in here. Okay, so you're going to have to do a whole bunch of substitutions. So step one is, since I'm looking for acceleration, I might as well sum in the x direction because that's where acceleration is occurring. And so I sum in the x direction. Actually, step one is to come over here and break that tension force into components. You'll look down into this answer. I see some sines and cosines and I see t. So I'm on the right track. So positive force minus the negative force equals mass times acceleration. This is in the x direction. So acceleration in the x direction is equal to t sine theta minus f over m. Can't have f in my answer, got to find f. Okay, well, what's the definition of f? Well, it's friction. It's kinetic friction equals mu sub k times, I use the symbols that they gave us, although I don't like it, n. But I don't know n. N's not in there. Mu is in there, so I've got to solve for n. How do I solve for n? I got to sum the forces in the y direction, and in this case, we don't have acceleration. Acceleration is 0. So summing the forces in the y direction, I have two positive forces, right? I have normal force and I have the component, don't forget that, in the from force of tension in the y direction, and I have the force of gravity, which is mg. And then solve for n, then plug that back into the original equation, and boom, I have my answer. This is exactly the same problem. Hold on. So hopefully pause your video if you need to look at my work, and then you can move on to the next problem. Number 9, same exact kind of problem, except this time they give you numbers, okay? Most of the time they don't, but every once in a while they do. And on free response questions, you might actually have to calculate numbers, okay? Same exact thing. I have been asked to determine the tension in the string. So I'll start with the fact that they gave me, this is super important. If I have a constant speed, that means my acceleration is 0. So let's go ahead and solve for tension in the x direction. All right, sum the forces in the x direction is all of those forces add up to 0. So this is my step 1. I found the positive force, t cosine 30 degrees, minus the force of friction. I went ahead and used mu sub Fn equals 0. I need to know tension. Okay, well, I don't know force normal, but I'm sorry, I don't have force normal, so I can't calculate that. I do know what cosine 30 is, so I need to solve for force normal. So I go over here, step 2, and I sum the forces in the y direction, and I get an equation for force normal using my Newton's second law. And I have two positive forces in the y direction, force normal plus tension times sine theta, which is 30 degrees, minus mg, which is my only negative force in the y direction. All those added up equals 0. Rearrange algebraically, solve for force normal, and then plug that back into my original equation. And then I have to do some algebra. When I was doing this quickly at home, I made the mistake of not including my negative as I distributed it through the second term in this little bracket. So be careful, make sure you don't make an algebraic mistake. If you distribute that through, you'll find that you can then combine 0.866 with 0.15 t, because those are the same terms. It's the same as 0.5x squared plus 1.2x squared. That would be 2x squared, okay? So those are the same terms, you add them, and then you solve for t, and t was 14.7 newtons, okay? Moving on. I have a situation. I have these blocks, they're all tied together, X, Y, and Z. They're hanging from a ceiling. If they're hanging from the ceiling, what do we know? They are in static condition, okay? Acceleration is 0, they're hanging. They didn't tell you that, but you should be able to see that from the picture. They're identical. That means the masses are the same. They hang from the string, and they want to know which of the following free body diagrams could represent the forces exerting on block Y. Well, the forces better equal 0 if I added them all up. Plus, I know that the force of gravity on Y is going to equal force of tension on pulling downward. I called it T2. How did I know that? Because if I drew a free body diagram on block Z, I have T2 down and I have force of gravity down. Well, they have the same mass. So force of gravity on block Z is the same as T2, which is the same as force of gravity on block Y. So I hope that makes sense. So T1 upward better be twice, better equal the same magnitude as if I took force of gravity plus T2. So it's longer because I have to have a net force of 0. And if I go through here and look at the answers, first off, A should immediately not be a possibility because there's no T2 on there. Secondly, B, that one's the correct answer. I looked at tension up. I counted the number of blocks. That's 4. I looked at the other 2 vectors. They're 2 each. 2 plus 2 is 4. That's a total downward of 4, so they cancel each other out. If I look at C, there's a net force downward. That would indicate that the block is accelerating downward. D, that would indicate that the block is also accelerating downward. Not possible because it's hanging and a static condition. Number 11. At first, when I looked at this, I was confused when they told me that there were 2 answers. And they stumped me for a nanosecond, and then I got it. Okay, so I have this information. They don't tell me anything about what the block is doing. They tell me there's a force of gravity, force of friction, force applied, and a normal force. And they tell me that which of the following could represent the net force that's exerted on the object. Select 2 answers. So option 1 was my first immediate answer. And I thought that was the only answer. And I thought they made a mistake. And 99.9% of the time, they don't make a mistake, and it's me. So here's option 1. And this is probably what you thought of as well. Force applied to the right, force of kinetic friction to the left. Because I have an unequal balance, I would assume that you also would know that I'm accelerating to the right. And since it's, I don't know, well, it's accelerating to the right. It could have a velocity of 0, or it could be moving to the right and speeding up, but it's going to accelerate to the right. That's what we know. It's speeding up. So the net force in that situation is force net is 8 minus 2, which equals 6. Okay, so that's A. So that one you should have got rather quickly. Most likely that's what you were thinking of. What about option 2? This could also be happening. I could be actually, here's my table, and force of friction could be to the left, and force applied could also be to the left. And, well, wait a minute, Mrs. Carrieri, force of friction has to be opposing motion. Okay, well, velocity could be positive to the right, and my force applied to the left, so I'm actually slowing down in the situation, okay? So my net force is negative 10 newtons because I have both of my force of friction and force applied are negative. But they ask for the magnitude of the net force, therefore it's 10. So that one was tricky. I would agree. Number 12, an object travels down a ramp at constant acceleration. Not A equals 0. Okay, come on. Constant acceleration. Oh, no. A does not equal 0. That's what I said. Okay, the object experiences a force of friction and a gravitational force. Which of the following could be true about the motion of the object? So quickly here, I have a picture. It's on a ramp. The acceleration is not 0, and the velocity is downward. So here's all the forces. If it's not 0, then that FG sine theta, which you should be able to see and quickly draw that picture, FG sine theta, remember that theta ends up underneath there. FG sine theta must be greater than force of friction, okay, if it's accelerating downward, which it said it did. It was constant acceleration. So that there has to be a net force. So now let's look at the answers. The force of friction between the surface and the object is less than the component of gravitational force that is parallel to the ramp. Force of friction is less than FG sine theta. This is true. That is true. And so if you believe it, I mean, since you know that's true, you could, because I have to have acceleration, I could quickly circle A and move on. But just for chagrins, let's go through each one. B was the hardest one to see, so I'm going to skip it. For B was the hardest one to visualize or justify in my head. But let's look at C and D. If the object's mass is if the mass is increased, the normal force exerted on the object would remain the same. So let's look at that. Force normal, which is equal to Fg cosine theta. As force normal goes up, so does Fg, and so therefore Fg cosine theta goes up. So that's not true, okay? D, the force of friction acts in the same direction as the object travels. That is never true. That is never true. Yes, it's always opposing motion. I was looking at the one above, but that's still correct. It was moving to the right, slowing down. Okay. And then B, if the object's mass is increased, the object's acceleration would change. Okay, that one I had to think about. If the mass goes up, force of gravity goes up, which means force of gravity sine theta goes up, which you would think the acceleration would change. But there's a force normal in the equation for force of kinetic friction, and force normal is equal to Fg cosine theta, which because the mass went up, Fg cosine theta went up. So the amount that force of gravity sine theta goes up is the same amount that force of kinetic friction goes up, so the acceleration did not change. Okay, that one's harder to see. All right, that's the end of my video. I hope that helps.